Okay, everyone, welcome back. At the end of lecture last time, I had finally introduced analytic functions. So let me bring that sheet back. So here's the definition I gave. Function of a complex variable is analytic at a point z0 if it has a derivative at each point in some neighborhood of z0. And I also mentioned that there are some alternative terms here. So f of z is holomorphic at z0. This means the same thing. F of z is regular at z0 means the same thing. So I will use these interchangeably. The most common one that I'll use interchangeably is saying that it's holomorphic. Um, and the definition of being analytic on an open set is if it's analytic at every point in the open set. That is, it has a derivative everywhere in that set. If we talk about a function being analytic on a closed set, then the idea is that it is analytic on some open set that contains that closed set. That's what is meant. The notion of a function being entire is being analytic on the entire complex plane. Okay. Um, and before I move on with some other related definitions here, I wanted to address the fact that we've used this word analytic, which, um, depending on how much real analysis you've had, you may have already encountered this word in the context of real valued functions of real variables. And in that context, it has a very specific meaning. So this part is a total aside for now. This is not addressed in the in our textbook yet. As an aside here, let's go to the world of real analysis. So in real analysis, that is, calculus of real valued functions of a real variable. Okay. Uh, what does analytic mean? So in real analysis, analytic functions are functions that have power series expansions. In neighborhoods of the specified point. Okay. What do I mean? If a function, say f of x, is analytic, then at some point, say x naught, then it has some power series expansion, which means that I can view this f as some power series in a neighborhood, say, of x naught. Right, so it looks like that. So if I have an x, or if I have some x that is close to x naught, then near that x naught, I can actually think of my function as a power series. And now, what is it that I get from this? So being analytic, so we're going to ignore the definition of analytic that I just mentioned for functions of complex variable, and we're just going to focus on this. So this is an example of an analytic function of a real variable. And being analytic in real analysis is basically the nicest property that a function could have, because the second that you have a function is equal to its own power, or is equal to this, I was about to say equal to its own Taylor series, which is fine too. But once you have a function that is that has a power series expansion, this is really, really, really nice because, for instance, this immediately implies, using term-by-term differentiation, right? This immediately implies that f has infinitely many derivatives. Uh, which is f is smooth, right? Or you might have seen it written as f is c infinity. Okay, where C0 is just being continuous, C1 is having one continuous derivative on some specified set. So C infinity is having infinitely many derivatives. So if f is analytic, then f has infinitely many derivatives, because you can just use term-by-term differentiation here and find any amount of derivatives that you like. So you are good to go as far as this goes. Now, in real analysis, unfortunately, the opposite direction is not true. But, so in real analysis, right, the implication that f is smooth, or f has infinitely many continuous derivatives on some domain, does not imply f is analytic. Okay. So this is false. There are many examples of this. What's an example I can think of? If you pick this, right? That works. So here's an example. Okay. Does that work? Yeah, that's fine. Being being smooth, that is having infinitely many derivatives, does not guarantee that that the function has power series expansion near some specified point. And so, because of that, even having infinitely many derivatives is not enough to guarantee a function being analytic in real analysis. Okay. Although the other application is immediate. So yeah, the other direction is something that you do get, but you don't get this direction. So even having infinitely many derivatives doesn't mean you're analytic. Another fact that you don't get, right? Also, having n derivatives does not in any way tell you that you have n plus 1 derivatives, right? And this is for functions of a real variable still. So for instance, if I know that f is continuous, say, and we'll say that f prime of x naught exists and f double prime of x naught exists, and so on, all the way up to the nth derivative of x naught exists. And even if I know something about existence, continuity of these things, the function itself is continuous at the point, blah, 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 I would need some other crazy stuff to actually guarantee that the n plus first derivative at x naught exists. So you can cook up various examples of functions, of course, that have any number of derivatives you like at some point, first, second, third, fourth, all the way up to, say, fifth derivative, but then its sixth derivative, right, is discontinuous at that point. Okay, you might already, be thinking of some examples now, just based on some basic example of, a function that is smooth enough to be okay having a couple of derivatives at a point, but one more derivative and you've gone too far and the function's broken, right? Typically, right, it's thought of in real analysis that taking derivatives, differentiation breaks functions, right? You're reducing the regularity of the function. Every derivative you take, right, is like reducing the regularity. Now, of course, there are smooth functions. They have infinitely many derivatives, and so it's fine to take as many derivatives as you like. But in general, differentiation is like reducing the regularity or breaking the function in some way. Okay. So the reason that I wanted to mention this about real analysis is the following fact. So it turns out that in complex analysis, this is completely different. Okay. And I cannot stress enough how different this is. Okay. So here is the point. In our beginning definition of what it means for a function of a complex variable to be analytic, we didn't use this word randomly, even though we haven't referred to power series here yet. We didn't use this word randomly. This word is used in the exact same way that it's used for real analysis. Okay, and so it turns out that if f of z is analytic, we'll say on some domain D, then it has a power series expansion. On D. Okay. And thus has infinitely many derivatives, or has derivatives of all orders on D. So first fact, it has a power series expansion on D. We'll talk about that later in this course. Okay, but not yet. And thus has derivatives of all orders on D. So this analytic on D is analytic in the sense that I defined at the beginning of this lecture and at the end of the previous lecture. This one. But being analytic at a point z0, the definition was just that it has a derivative at each point in some neighborhood of z0. Has a derivative. That is, f prime of z exists, right? And so in complex analysis, what I'm saying is that f prime of z exists, say at all points, at each point in some neighborhood of z0. This implies that this exists at each point. I'm not going to rewrite all that. Right? For all n, right? All derivatives you want to take here work out. And also f has a power series expansion on D. Okay. So look how different this is, right? For for real functions, okay. First of all, even having infinitely many derivatives doesn't guarantee that f has a power series expansion, right? Furthermore, even having one derivative says nothing about having two derivatives, three derivatives, four derivatives, and so on. Okay. But in the complex case, having a single derivative gets you all derivatives, right? You actually have infinitely many derivatives, okay? And you have a power series expansion, right? So this is totally different. This is completely different. It is almost as different as it could be in terms of regularity properties. Okay, and so weirdly enough, for functions of a complex variable, having one derivative, okay, implies the existence of derivatives of all orders, and even better than that, gives you a power series expansion. Okay. And so a lot of the tools that we're going to use later to analyze functions are going to make use of this fact that being an analytic having that single derivative, making you an analytic function, means that you have a power series expansion. And then you can do all kinds of computations with that. Okay. And so now we're back into the realm of functions of complex variables. So when I say analytic, I just mean that it has a derivative at that point. A lot of times in a complex analysis course, you start out with the definition that a function's holomorphic if it has a derivative at that point, and then later it's shown that if you define analytic to mean it has a power series expansion, then a holomorphic function is analytic necessarily, and an analytic function is holomorphic. That's an even easier direction to do. And so you prove this theorem that holomorphic and analytic functions holomorphic if and only if it's analytic in that sense. And so you can actually, if you want, just define analytic to mean that it has a derivative at all points in some neighborhood of a point. And so that is what we're going to do in this class. That's what the textbook does, and that's what we are going to do. Okay. And so here's some examples, right, that are easy. For instance, if you look at a function that is just 1 over z, this is analytic at every non-zero point in the finite plane. So this is analytic at every non-zero point. Okay. Let's look at the function, say, that is the modulus of z squared. This is actually not analytic at any point. We know that it only has a derivative at z equals 0, but it doesn't even have any derivatives in any in any of the points that would be neighborhood points of 0. And so this is not analytic at any point. Right? Not even z equals 0, right? Because that's the only place it has derivatives, so it has no derivatives in the in a neighborhood of that point. Okay. If I take my function to be a polynomial, so a0 plus a1z plus a2z squared all the way up to some a sub n z to the n, this is analytic at every point in the complex plane. Okay. I.e., this f of z is entire. Right? Of course, it's generally true for any polynomial, this form. So, for instance, this is the statement that polynomials are entire. Okay, so a polynomial is an example, one of the simplest examples of an entire function. Okay. All right. Now, picking out this first example that we went with, it is analytic at every non-zero point. At 0, it is not analytic. So when something like that happens, not necessarily that it's analytic at every single point except one point, but when it's analytic at every point in a neighborhood of some point except at that point that the neighborhood's centered at, that is a special thing that is going to, that setting is going to come up quite frequently in this course. And so this needs to have a special name. So definition of a singular point. Okay, is the following. So if f is not analytic at z naught, but is analytic at some point in every neighborhood of z naught. Okay. Then z naught is called a singular point. Okay. Or singularity of f. Okay. And an example of that is the following. So f of z equals 1 over z has z equals 0 as a singular point. Okay. All right. But be careful not to use singular point as kind of a synonym for a point where the function is has a derivative that's not defined, because that's not really what's going on here. And so an example of that is if you look at this function, which is mod z squared. So this is modulus of z squared. What do I get here? Well, this has no singular points, right? And it has no singular points because it doesn't. It's not analytic at any point, right? Not even z equals 0. It has a derivative at a single point, z equals 0, and no other points. And so by definition, it just fails to have any singular points, right? So it has no singular points. Okay, so a lack of singular points in no way guarantees anything about being analytic or having derivatives that are nice. Okay. All right. And so the question is, how do I know if a function is analytic? I refer to my previous theorems on functions having a derivative that exists at some point. So my conditions for a function being analytic are given by the previous theorems on existence of f prime of z naught. Okay. All right. But we have some nice facts that allow us to build examples of analytic functions from the derivative rules. All right. But my derivative rules provide easy ways to build analytic functions from analytic functions. So what do I mean by that? Things like the fact that derivatives break up across sums. You can pull constants out of derivatives. You have the product rule, the quotient rule, the chain rule. All those things guarantee you your functions being analytic if you start with analytic functions and you use those combinations. So my derivative rules provide easy ways to build analytic functions from analytic functions. So this is a nice fact. If you're looking for examples of analytic functions on your own, this is one way to build those examples. Okay, so then what do I get from this? So one, if say f and g is analytic, then this implies that f plus or minus g is analytic. Okay, so if you start two analytic functions, their sum or their difference is analytic, right? So this, defining this pointwise, you get another analytic function. Same thing is true I'm not going to even rewrite that. This means that their product, f times g, is analytic. Same thing is true using the quotient rule. For the quotient, f over g is analytic. But of course, there's an extra thing here, but it's analytic on any domain where g is not 0. And as you might be able to guess, this is also going to provide you an easy way of coming up with examples of singular points. Okay, by judiciously picking a denominator function here that has zeros in some domain that you're looking at. Okay. All right, and so this one is nice because this actually tells you that from our earlier comment on polynomials being entire, this also tells you that a rational function that is polynomial over polynomial, right? A rational function p over z over p of z over q of z is analytic on any domain where q is not 0. And so this is a very important fact because these rational functions are going to be very important examples for us going forward. Okay. So again, using the same derivative rules, it's true of the chain rule. So number 4, chain rule implies that if f and g are analytic, and of course the image of f lies in the domain of g, so all those things happen so that this thing is well defined. I'm not going to worry about that too much. So if f and g are analytic and it actually makes sense to form the composition, then say g composed with f, right, or f composed with g, whichever one is going to the domain of the other, then g composed with f is analytic. So composing two analytic functions gives me an analytic function. Okay. All right. So that's good. Okay. Now, what can I say here? Should I? So this theorem, maybe I'll mention this theorem, and then I'll mention another theorem that I'll talk about later in the course, but it's just another example of how things are different here. And maybe it would be more satisfying if I kind of left it as a secret and did it later as a sort of surprise, but I think I'll actually go ahead and include it after this theorem. Just because it's so interesting, and I can hardly contain myself. I have to go ahead and ruin the fun by letting you know early. So what if I have a derivative that is 0 everywhere in a domain, right? So if f prime z is equal to 0 everywhere in some domain D, then, well, what did we know about this for real valued functions? I mean, we knew exactly if we had a function like this that had 0 derivative everywhere, then this is a constant function, right? So we want to show this is also the case for complex functions. So this then f of z must be constant on z, or sorry, on D. D is my domain. Okay. So this proof isn't too bad. I'm going to leave out some of the details just because technically this is part of this is something that you could do earlier in Calc 3. But first of all, I'll say if we write f of z in the usual way as u plus iv, then if f prime of z is equal to 0, what does that mean? Well, first of all, this would mean that the x partial of u plus I times the x partial of v is equal to 0 everywhere on D, right? By Cauchy-Riemann, what does this mean? This also means that, say, Vy minus Iu sub y is also equal to 0. Okay. And, of course, by identifying these using Cauchy-Riemann or whatever you like, we have that u sub x must be equal to u sub y, which is 0, and v sub x is equal to v sub y, which is 0. And so the derivatives, these partials of u and v, are also 0. Okay, and this is true everywhere in D. Okay, because these relationships are true everywhere in D. All right. Okay. Now, here's a question. One is that how can I actually tell what it is that is going on, or what this function is doing, okay, on D? Well, I can't graph this thing, right? But I can talk about how, say, it transforms some region, okay, in the plane. Okay, so here's the plane. I can talk about how it transforms some region here. And so, what do I know about how it transforms some region? Maybe this is what my region D looks like, right? This is kind of how the one drawn in the textbook looks, and it's drawn like this to stress there's a particular property of this that is going to be used here in this next fact. Okay, and it's the following. So fact, okay, for instance, u of xy is constant along any line segment L extending from a point P to a point P prime lying entirely in D. Okay. Now, how do I show that? I can show this using the directional derivative. So the proof of this little subfact is using directional derivative from Calc 3. Okay, and so just a little refresher. Directional derivative in the direction of, say, some unit vector is given by gradient of function dotted with that unit vector. But, of course, the gradient of u has 0 as both components, for instance. And so what this means is that u is actually constant along any line segment, and this is easy to show. So if here's my p, and my p prime looks like this. Of course, I didn't want to pick a p prime here because then this line segment connecting them wouldn't lie in it. But any line segment L like this, if I pick a unit vector, say lying parallel to L, I can show that the directional derivative at that point, pointing in the direction of the unit vector, is just going to be it's just going to be 0. Okay, it's just going to be 0 because the gradient is 0 in both slots, and so you're dotting whatever this unit vector is with 0, and so you get 0 for your directional derivative there. Of course, you can actually do the same thing for v. This is also true for v. Okay. And so this fact that I've boxed is true for both u and v. These are real valued functions of two real variables, right? Okay. Huh. How does this help me? Okay. How does this help? Well, so what am I, the second I move to this fact about the value of, really I'm talking about the value of f. So I'm talking about u, but I proved this for u and v. If I show that u and v is constant along any of such line segments, and so is f. Okay, but how does that help me? Well, this D is a domain, right? So this D is a domain. Remember what the definition of, when we say the word domain for a set, that had a special meaning for us. So a domain was a non-empty open set. So I've drawn it as an open set, and I've drawn it as a non-empty set that is connected. And our version of connected was that any 2 points in D could be connected by some finitely many line segments, right, lying entirely in D. Okay, and so since I have that f is constant along any line segment connecting, say, 2 points in D lying entirely in D, and since any 2 points in my domain D are connected by finitely many such line segments, and my function f is going to be constant along any of those, what do I get? Right? I get that a way of constructing this image is always the same, right? So there must exist constants a and b such that u of xy is equal to a and v of xy is equal to b on D. Thus, f of z is equal to a plus bi for all z in D. Thus, it is constant. It is that constant complex number for all points z in D. Okay. Now, what we did here is actually kind of our first example of a fact that later I'm going to talk about a general fact of how we can specify values of an analytic function knowing, say, its values along certain line segments or along certain subdomains. I'm going to talk about that later at the very end of this chapter. But this is kind of our first example of doing that. Okay. All right. So let's talk about some easy examples of analytic functions. So for instance, if I look at the rational function, say z cubed plus 4 over z squared minus 3, z squared plus 1, what kind of function is this? This is analytic on the complex plane, except at the points z is plus or minus the square root of 3, and z is plus or minus I. Right, so that's the zeros of this part. This is the zeros of the other part of the denominator. And these points are singular points of f. They're singular points because this thing is analytic at every other point. Okay, we get that it's analytic at every other point by just its form, right? It's a rational function. It is a ratio of two polynomials, and those polynomials are entire, right? But the denominator is 0 at these 4 points. Okay. And because it is a quotient, I can use the quotient rule to get the formula for the derivatives that I need to show me that the derivatives of this exist everywhere except these points. Okay. All right. What about if I have a function? So if I wanted to show that this was analytic, what could I say? So one, I could just say, by the quotient rule, for instance, I know that the derivatives exist everywhere except these points, and that gives me analyticity of this thing. Now, if I actually wanted to, so that's all you have to say say that this is analytic everywhere except these points. Now, if you actually wanted to compute its derivative somewhere, well, then you would need to actually apply the quotient rule. You wouldn't just say that since you actually want to know what f prime of z is for some z, then you would actually apply the quotient rule and find the formula for that thing. Okay, oh, that's not a clean sheet. Okay. So what if you have a function that's actually given to you in terms of its real and imaginary parts, so in terms of x and y here. So let's look at, for instance, the function that is hyperbolic cosine of x times cosine y plus I times hyperbolic sine of x times sine y. Okay, so let's look at a function like this. And so we have component functions u of xy, which is cosh x cosine y, and v of xy is sinh x sine y. Okay, so how would I show that this thing is analytic? I want to just look at Cauchy-Riemann equations to make sure that they are satisfied. So what is the x partial of u here? X partial of u is the derivative of cosh x. That's just sinh x. So this is sinh x cosine y. Okay. So what is the y partial of v? Y partial of v is sinh x, derivative of sine y is cosine y. So this is sinh x cosine y. This is exactly what I have there. All right, so that's good. What about u sub y? So this is cosh x times the derivative of cosine y. The derivative of cosine y is minus sine y. So this is minus cosh x sine y. Okay. Well, what is the x partial of v? The x partial of v is cosh x sine y. And I have minus cosh x sine y here, so I have minus the x partial of v. So Cauchy-Riemann is satisfied. This is satisfied everywhere. These are satisfied. So Cauchy-Riemann is satisfied everywhere. What does that mean? This means that f is entire. All right, this is directly from those theorems that we talked about before the definition of a function being analytic, that allowed us to say, oh, well, here, our function has a derivative at all points on the complex plane. Okay. So let's do another example here. Okay. Suppose that both f of z, which I will write in the usual way, so u of xy plus I, v of xy, and its complex conjugate, which as a function is f of z bar. So this is u of xy minus I v of xy. So suppose that both f and f bar are analytic on D. Sorry. Okay. So both of these, both function and its conjugate, are analytic on D. Then f must be constant on D. Okay. Why is this the case? Okay. Well, one thing is we can write this f bar function as big U of xy plus I times big V of xy. Okay, pretending like we don't actually know exactly what these things are, just to keep it separated, looking at, say, Cauchy-Riemann, for instance. Okay. Of course, we know that big U is just equal to little u, and big V is minus little v. Okay. So then, what do I know? Right. Well, by Cauchy-Riemann, right? Let me leave this on the screen here. So by Cauchy-Riemann, okay, and of course we have the Cauchy-Riemann satisfied because both of these things are analytic. So by Cauchy-Riemann equations, we have u sub x is equal to v sub y, and u sub y is equal to minus v sub x. And for f bar, we also have that big U sub x is equal to big V sub y, and big U sub y is equal to minus big V sub x. Of course, notice then that because of what I've boxed here, that big U and big V are actually just little u and minus little v, then what do I get from these relations? Well, actually, I can rewrite this as u sub x is equal to, right, so big U sub x is actually just little u sub x. Big V sub y is actually minus little v sub y. So not only do I have that u sub x is equal to v sub y, it's also equal to minus v sub y. Okay. All right, but also little u sub y is equal to v sub x. This is just from this because big V is equal to minus little v. So this is minus minus, so this is little v sub x. So not only is little u sub y equal to minus little v sub x, it's actually equal to positive v sub x. So it's equal to thing and minus thing. What does that mean about these things? Well, this means that u sub x is equal to 0. V sub x is equal to 0. And these things also imply that u sub y is equal to 0 and v sub y is equal to 0. So then, what does this mean? This means, since I can write f prime of z as u sub x plus I v sub x, this is 0 plus I 0, so this is just 0. And what did we just show previously? If I have a function, so this is on D, right, everywhere on D. I have a function that it has derivative that's equal to 0 everywhere on some domain D. This means that f of z is constant on D. Okay. All right. Okay, so here's a basic example of a type of fact that we might show like this. Here's another example that I'll leave it to you to show. So as exercise, okay, so put this in your next homework. If f is analytic on D, and f, or the modulus of f of z, is constant on D, okay, then f is constant on D. Okay, so this is true. Okay. We'll use this later in a proof. All right. Okay. All right, let me say one more thing that I'm not going to expound too much on. I just want to mention it because it's cool. So this is something we won't prove until later. So here is a theorem called Louisvilles Theorem. So won't prove until later. If f is both entire and bounded, what does bounded mean? Remember, bounded, we used, our definition was that its modulus is less than or equal to some real number, m. Say for all z, if we said that it's bounded on D, then that would be for all z on D. When we just say it's bounded period, that would just be for all, for all z. So for all z period, if it's just bounded, if it's bounded on some domain, then that would be for all z in some whatever domain. Okay. If f is both entire and bounded, then it is constant. This is another massive difference between complex and real analysis. So note, this is another huge difference between complex and real analysis. Since this theorem is clearly false for real valued function, or for real valued functions of a real variable, since this theorem is clearly false for functions in real analysis. So how do I see that this is clearly false? Well, so this is, I misspelled the name here of Louisville's theorem. So the I goes before. There we go. Knew something was wrong there. Okay. So you can notice that, for instance, this is very false on the reals here, because I mean, literally pick whatever you like here, right? So I mean, how about this, right? F of x is like 1 over x squared plus 1. Yeah. Right. So this 1 over x squared plus 1 is bounded. So this thing is bounded below by 0 and above by 1. So right. So 0 is less than or equal to f of x, which is less than or equal to 1. So it's bounded, and entire, since it is differentiable, and continuous, of course, on the entire real line, but definitely not constant. Right, so f of 0 and f of 1 are different numbers. Okay. All right. So here's a quick example showing how wrong this theorem would be for real analysis, right? It's just clearly false, not even close to true. Okay. But this is a theorem in complex analysis. Any entire and bounded function is constant. Okay. So this is again signaling to you just how different the picture is for complex analysis. Okay. The good news is that, as I mentioned at the beginning of this course, it's not that intuitive that this would be the case, but in so many ways, complex analysis is a lot nicer than real analysis. Okay, things work out more nicely in general. Okay. All right, so those are the main things I wanted to mention about this. So now I want to talk a little bit about harmonic functions. It is hard to progress, or I should say it's not really even that sensible to ignore harmonic functions showing up in early complex analysis. And so we have a definition of harmonic functions. Okay. So a function, we can define this for real valued functions of any number of real variables, but we'll just talk about it for two real variables first. So a function, we'll say big H of xy of two real variables is said to be harmonic on D if it has continuous first and second order partials on D, okay, and satisfies the partial differential equation known as Laplace's equation. What is Laplace's equation? It is that the double x partial of h plus the double y partial of h is equal to 0. Okay. We can rewrite this as delta of h is equal to 0, where this delta is the Laplacian operator. You might have encountered this operator before. So physicists will use a different, sometimes they use different notation for this. They'll use nabla squared, right? Instead, this is better. So yeah, so this is the Laplacian operator. So sometimes, like I said, you'll see it written like this, but this is how it's written. This is useful for remembering for an example of where this thing comes from. So a couple of ways to look at this. So note that, for instance, the Laplacian of, say, a function. Well, I'm using f as a function of a complex variable here, so I won't write that. So notice that like delta of h is the same as the divergence of the gradient of h. Okay, and so if you're using physics notation for the divergence, which is nabla dot, right? This would be like nabla dot nabla h, so nabla squared. That's where this comes from. So Laplacian of h is the divergence of the gradient of h, or here, if I write this out, whatever. If I write this out as divergence of the gradient of h. Okay. Another way of looking at this is that Laplacian of h is equal to the trace of the Hessian matrix of h. Okay. These are two ways of seeing where this arises. Okay, so thinking about it as the trace of the Hessian matrix of a function, h is just the collection of second order partials, right? So Hessian is symmetric if the function's nice, and second order partials commute at a point. And the trace of that matrix, that is the sum of its diagonal entries, is the Laplacian of h. Okay, so I won't even talk about how useful harmonic functions are in a variety of settings. So harmonic functions are extremely useful in all kinds of contexts. If you're interested in like signal processing or well, really any number of applications, harmonic functions show up unexpectedly and expectedly. And so this is really important. The textbook mentions a couple. So yeah, temperatures in thin plates lying in the xy plane are often harmonic. A function's harmonic when it denotes electrostatic potential. It varies only with x and y in the interior of a region in 3D space that's free of charges. So anyway, there's that is not by any means exhaustive. Harmonic functions show up all over the place. And so, but in our like why we are interested in them is the following. So if a function f of z is analytic in a domain D, then its component functions u and v are harmonic on D. Okay, so a basic example of harmonic functions comes from functions that arise as real and imaginary parts of analytic functions of a complex variable. Okay, and so the proof of this is actually not too bad, right? So we have Cauchy-Riemann, right? So by Cauchy-Riemann, what do we know? We know that u sub x is equal to v sub y, and u sub y is equal to minus v sub x. Okay, well, let's differentiate both sides here, say with respect to x. Okay, so if we take further partials, we have that u sub xx is equal to, say, v sub yx, and u sub yx is equal to minus v sub xx. Okay, if we differentiate with respect to y, of course, we also get u sub xy is equal to v sub yy, and we also get that u sub yy is equal to minus v sub xy. Okay. Okay. Now, if functions of two real variables are nice enough, I won't state the exact thing required here, then the partials commute. i.e. It just needs to be nice enough at a point for them to do it, but it's nice enough on this entire domain. These are going to be nice enough on that domain. The partials commuting, that just means exactly what you think it means. So i.e. u sub yx is equal to u sub xy, and v sub yx is equal to v sub xy. Okay, this was a thing that maybe after like one example in Calc 3, something was said, maybe even this was stated exactly what was needed. If not, there was some hand waving done, and you know, were shown that, okay, yeah, here's an example of where they don't commute, but if your function's nice enough, then you can always just assume that they commute there, and most of the functions you're going to be dealing with, say in Calc 3, are going to satisfy that, so you don't have to worry too much about it. So I'm going to do the same thing here. So these things commute, okay, in general, when you have nice functions. So because these things commute, what do I get here by swapping the order? So first of all, u sub xy is the same thing. So I'm looking for what u sub yy is. So u sub yy is minus v sub xy, which should be minus v sub yx. That's u sub xx. And so I get u sub xx is equal to, say, minus u sub yy. Or maybe the minus is on the other side, the way I read it off there. And also I get that v sub xx, or minus v sub xx, is equal to v sub yy. So u sub xx plus u sub yy is equal to 0, and v sub xx plus v sub yy is equal to 0. So u and v are harmonic. Okay. So basically, this is just some bookkeeping with using Cauchy-Riemann and being careful here with the substitution that has to happen. Okay. All right. Okay. So what are some examples where we can use this fact? So one is if f of z is given in terms of its component function. So if I have e to the minus y sine x minus I e to the minus y cosine x, you can show that this is entire. Okay, so this is entire, so it's analytic everywhere. Thus, both its real and imaginary component must be harmonic, but we can even just focus on the you know, on its real part. So thus u sub xy, which is e to the minus y sine x, is harmonic, for instance. Also, its imaginary component's harmonic. Okay. All right. And of course, this is entire, so this is harmonic, you know, on any domain. So this is on any domain in the plane that you pick. Okay. Another example. So f of z is I over z squared. This is analytic. Whenever, I mean, I is just a complex constant, so the only potential problem here, just using differentiation formulas, is when z is equal to 0 is a problem. So whenever z is not equal to 0, this thing's analytic and it has derivatives everywhere else. Okay, and of course, if we work out what its components look like here, so if this is so I over z squared, we can think of as I over z squared times the modulus, or sorry, not the modulus, conjugate of z squared in this way. So this is, say, I of z bar squared over z times z bar squared. Okay, which I can of course write as the modulus of z squared squared. So this is I z bar squared over modulus of z squared squared. Okay. And so this is rewriting all of this. This would be 2, this would be 2xy, would be the real part of the numerator, plus I times x squared minus y squared. So we just swap the order of these things, divided by x squared plus y squared squared. And so if I take the real and imaginary part component functions here, this is 2xy over x squared plus y squared squared, and v of xy is x squared minus y squared over x squared plus y squared squared. So these are both harmonic on any d not containing 0. Okay. All right. So any domain D doesn't contain the origin. These things are harmonic. Okay. All right. So another term I wanted to define here in terms of harmonic functions. So definition: if u xy and v of xy are both harmonic on D, and satisfy the Cauchy-Riemann equations on D, then we say that V is a harmonic conjugate of U. Okay. And so this gives us a very nice way of restating the previous fact as an if and only if statement. So a function f of z, which is u plus iv, is analytic in a domain D. Okay, if and only if V is a harmonic conjugate of U. Okay. All right. So, this is this notion can be a little tricky because notice the way that I phrased this, and notice the careful phrasing here in the sense that V is a harmonic conjugate of U, and I will warn you against trying to swap the order here. Okay, so V is a harmonic conjugate of U does not necessarily imply that U is a harmonic conjugate of V. Huh. How could this be? The way that I phrased it, you might kind of sort of think that it's not, the symmetry here is not that important. So to see that this is an issue, I want to look at my component functions of z squared. Okay, and so this is a warning, right? If I look at f of z equals z squared, as my example, okay, then remember we've done this example several times. So u here is x squared minus y squared, and v is 2xy. Now this thing is entire. It's a polynomial, right? So this is entire since it's a polynomial. Okay, and so because of this previous theorem, this means that v is a harmonic conjugate of u. Okay, everywhere in the plane, right? But u is not a harmonic conjugate of v. Why? What function would need to be analytic for that to be the case? This is true since the function 2xy plus I times x squared minus y squared is not analytic anywhere. You can check for yourself that this isn't analytic anywhere. Right? For instance, check the Cauchy-Riemann equations. Okay, and so we actually can't swap the order of that notion. And so when they, in the usual sense of us writing f as u plus iv, if f is analytic, we say v is a harmonic conjugate of u. Okay, that's the order that we're going with. All right. Okay, so we're pretty much done with this chapter and ready to move on to applying this stuff to specific analysis of specific functions. So we can start, you know, the computation heavy part of, well, all of it's computation heavy, but so we can actually start computing some of these quantities that we're really interested in. So we're going to be blasting through the application of this stuff to our basic functions. So I'm more or less done with this second setup chapter, and then we're going to be starting. Like I said, immediately we're going to be talking about exponential function, logarithmic functions, and then we're going to go kind of from there on to. Our goal is to get to the Cauchy integral formula as quickly as we can and to apply it as much as we can, and then look at some consequences. All right. So anyway, that's the immediate goal. So I will see you all tomorrow.